There we go. So sorry, Surajit. I
No
lost track
problem.
of time this morning.
No problem.
All to
All
get
right.
it up.
You can go ahead and put up your thing. I'm going to introduce you.
Okay. So, want me to share my screen?
Yeah, and there's no problem with sharing. So you have all the permissions.
All right. I'm just going to share my desktop and then I can start the PowerPoint after the fact.
Yeah, great. All right. That looks exciting already. Now let's see. Okay, so let's get rolling. It's such a delight to introduce Phil Metzger. Actually, I met Phil a long time ago. I don't even remember where, but it's always been fun knowing him, and I've long been raring to invite him to this club. So Phil will talk about the physics of rocket exhaust blowing lunar and Martian soil, which obviously is a very important problem because at microgravity, anything blowing is not good. One sec, some people are trying to enter. Okay, all right. So to introduce Phil briefly, Phil did his undergraduate from Auburn in 1985 and a PhD he did much later from University of Central Florida in 2005 in physics. He's a planetary scientist at the University of Central Florida, performing research related to solar system exploration, predicting how rocket exhaust interacts with extraterrestrial soil, investigating the mechanics of soil, characterizing lunar and Martian soil simulants, developing laser-based sensors to measure regolith ejecta during lunar landings, and developing methods to extract ice and metal particles from lunar soil via beneficiation processes. Oh, that was a tongue twister. He was previously with NASA, where he led the agency's work in rocket blast effects for human-class missions. He co-founded NASA's biannual workshop in granular materials in lunar and Martian exploration, and is a founding member of the ASCE Technical Committee for Regolith Operations, Mobility and Robotics. He received the Astronaut's Silver Snoopy Award in 2010 and was selected as the Kennedy Space Center's NASA Scientist/Engineer of the Year for 2011. He was selected for the ASCE Aerospace Division's Outstanding Technical Contribution Award in 2016 and became a NASA Innovative Advanced Concepts Fellow in 2019. So Phil is all of that, and he's a statistical physicist, which is almost too much to ask for. And with that, it's over to you.
Okay, thank you, Surajit. Yeah, so I did my doctoral work on the statistics of granular materials. So it was very theoretical. And however, with the funding I had available at NASA, I had to work on very applied projects. So I was always trying to find a way to apply statistical mechanics to rocket exhaust blowing dirt. And we're working in a very I can't think of the word, intersectional field where we're trying to merge fluid dynamics, granular mechanics, and extraterrestrial environments and geology to predict what we're going to see on the moon and to interpret data that we've been seeing on the moon and Mars. Lots of contributors over the years. I can't read the whole list, but just to mention that this is not the work of a huge number of people. Okay, I'm going to try to go over an overview of the phenomenology of rocket exhaust blowing soil, why this is important, the sizes of the ejecta particles, where do they go and how fast, at what height does the blowing begin, how much material is blown, multiple engine effects, shock effects from launching off the moon, chemical contamination, and damage to hardware. Okay, so an overview of the phenomenology. Rocket exhaust is, of course, a supersonic flow of fluid, of gas. It's a compressible flow because it's above Mach 0.3, well above that. It's typically about Mach 6. But it behaves differently on the moon versus the Earth or Mars, because on the Earth and Mars, the atmosphere is substantial and that tends to collimate the flow into a jet, whereas on the moon, it expands broadly, fills the entire hemisphere under the lander. That causes different effects. So when it's a jet, you get very sharp pressure gradients on the surface of the soil, which can induce shearing in the soil and dig a deep hole, whereas on the moon, you get very broad pressure gradients, low amplitude in the pressure gradient on the surface, and therefore it does not induce shearing, and so you don't get the deep digging. And because of that wonderful feature, we get all these Apollo moon hoax people telling us we didn't really land on the moon because it didn't dig a hole. But we understand that from the physics. Okay, so the rocket exhaust, as it exits the nozzle, there's a continuum flow region where the gas is dense, so the mean free path length of the gas molecules is short relative to the features of the flow. And so we can use continuum flow models like Navier-Stokes, Reynolds average Navier-Stokes simulations to model it. But after it expands some distance, there's a surface named after the researcher Bird called the Bird breakdown surface. And outside of that surface, you can't use Navier-Stokes. So we use direct simulation Monte Carlo or any other number of methods that are different approaches to handling the Boltzmann transport equation. And those methods then are showing these results where we've got some internal shocks in the flow. We've got this standoff shock, this broad bowl-shaped shock above the lunar surface, and then you have a stagnation region at high pressure. Now, in the stagnation region, we really should go back to using continuum flow models again, because the pressure, the gradients, the transport gradients are so high that the assumptions of DSMC, the Monte Carlo method, are no longer valid. However, we don't have any mature models that allow us to go from a continuum flow to a non-continuum flow back to a continuum flow again, and then as it expands away supersonically, well, it's subsonic in this region, so pressure information can travel upstream, and then you go back to supersonic flow and rarefied again. And so we don't have any mature models. There is actually one model that can handle the transitions from continuum to non-continuum, called the Unified Flow Solver, but it doesn't have turbulence models in it. So the fluid flow itself is a challenge, and we don't have all the physics adequately solved and put into simulations just for the gas part alone. There's been very little research on the behavior of turbulence in these transitions from continuum to rarefied flow and back. In fact, I only found one paper when I first researched this about 10 years ago, one paper, and it was a corporate paper that I couldn't access. Okay, so moving on to what happens when this gas flow interacts with the surface of the moon or another planetary body. So this is the case where it's a broad plume expanding in a vacuum, so it's not a jet. And you have the flow is stagnant here, but it expands to supersonic speeds again as it flows radially away from the center line. And underneath this shock wave, it's sort of like a converging, diverging nozzle again. So the gas flow converged into the stagnation region, then it diverges again as it goes out, and it goes supersonic again. And then there's a region of maximum shear stress where the density times the velocity squared, where the dynamic pressure is a maximum. And in that region is where you get the erosion, not directly under the nozzle. So you get an annular erosion pattern. But because the vehicle is translating as you're landing, that erosion is spread over the surface. So it spreads the erosion over a wide area, and therefore you don't see a crater, which gets all the moon hoax deniers excited. Now we've done simulations of the blowing soil and using the codes that are available. And so this is actually just doing Lagrangian simulations of the particles where you track the individual particles as discrete objects, calculate the dynamic forces on the particles in every time step, and then you time step and integrate the trajectory. And this is a high fidelity plume flow code, but it neglects all the particle collisions of all the different size particles. But such as it is, this is predicting, this is the Apollo lunar module, this is a side view, this is the plume, it's eroding right here, this is Surveyor crater, this is Apollo 12, the Surveyor spacecraft was located right here. We landed 160 meters away from the Surveyor spacecraft, and this rocket exhaust blows the ejecta, according to the simulation, at over 3,000 meters per second, which makes sense because the rocket exhaust is traveling about 3,100 meters per second. So the finest particles get up to the speed of the rocket exhaust, and this is well above lunar escape velocity. So any particles that don't hit terrain are going to fly right over the horizon and go into orbit around the sun. And you blow a dust ring around the moon, and a dust ring goes into solar orbit every time you land on the moon. But the surveyor was sandblasted by this effect. Now, according to the simulation, the ejecta should have gone right over the surveyor and not even hit it at all, because the surveyor was below the ejecta spray. But I'll talk more about that later. Okay, so we have images of these phenomena. In the Apollo lunar module, there was a camera mounted in the window. It was a film camera. The company that made the film no longer exists. The company that made the camera no longer exists. And so we're trying to interpret film from 40 years ago, and it's very difficult. Let's see, I'm not sure if this video is going to work. Okay, what I'm going to do is I'm going to stop the video, stop the presentation, and I'm going to get the video to play because it's really important to see this video. Give me just a second. I gotta get that. I thought the video was linked, but it's not linked. Let's see, movies.
Yeah, it should work from your regular screen.
Yeah, I just need to locate it on the disk, and then I'll play the video, because it'll be really, really good to see what an actual event looks like.
Yeah.
So I'm looking through my folders right now, and I'm in my video folder. Okay, here we go. Okay, there it is. And let me share the screen again after this opens. Okay, so this is going to be the view looking down from the lunar surface. No, I don't want to install an update. Okay, let me pause it and restart it, and then share the screen. Okay, let me share the desk. Oh, here we go. There's the video. Okay. All right, so this is the view looking out the window. This dark shadow on the upper left is the frame of the window, and you can see the craters. You can't really tell how high you are by the craters, because at any height they pretty much look the same. It's a power law size distribution of craters, and so you can't get a height scale from the image. But this is probably about 100 feet up. You can see the dust starting to blow. It gets hazy in the lower corner. You see streaks of dust. The streaks are wavering. Here's the shadow of the foot pad, the soil contact probe shadow. The foot pad, you can see the shadow on top and below the dust. And then the big blast of dust, there's dense flow. And then it takes about 30 seconds for the haziness to clear away. So I'll let that play again. You see the haziness, the smooth flow phase, then you get the streaking flow phase. Now the shadows from the
right now, I see a white screen for some reason.
Oh, okay, I'm sorry. Okay, because I maximized it. Okay, I won't run through it again. We'll move forward.
Okay.
PowerPoint, where's my PowerPoint? Okay. Okay, so anyways, here's the phases of the flow. You get before the plume effects, you have a loss of contrast in the image, but there's a haziness. We call that the smooth flow stage. And then you get streaking stage. This is where the terrain objects are large relative to the shock wave, and so you start to get enhanced flow around discrete objects under the shock wave. The streaking stage becomes more developed. You get finer streaks. You can see the shadow. This is the leg, and here's the shadow of the foot pad. And you have one shadow of it on top of the dust, another shadow of it on the surface below the dust. And that Also, that enables us to measure the geometry of the blowing dust cloud, which I'll show you in a moment. Then we call this the terrain modification stage, because this is where you're blowing out bulk quantities of material. Before I said you don't get erosion directly under the lander. That's not exactly true. We see a blast, a dense blast, even in the Apollo cases, where it blows away the upper surface layers of the soil, and it's opaque. So we can't measure any details in the flow, but we can see that it's opaque. So we want to fly lasers to shine down into that cloud to get more data. And then it takes about 30 seconds for the haziness to clear away, which is a mystery because the ballistic trajectories of the dust particles should clear within 2 to 3 seconds. So we don't know if it's electrostatics or if it's outgassing of the dust from the soil or some other factor. My personal favorite now is that the shutoff of the engine causes a low velocity shock wave, which launches particles on slow trajectories. And so that's what I think it may explain it. Okay, we do see rocks blowing. So we've found rocks in the videos. We tracked them from frame to frame and calculated their distance traveled. And from that, you can extract the velocities. We can also see these things we call dust tails. On the lunar surface, you see these sudden streaks appear, and they last for only 1 to 2 frames of the video, and then they disappear. They don't translate, they stay fixed on the surface. So we can explain that, which I'll do in a moment. We also see blowing dust clods. So these dust clods are moving relative to the lunar surface. They're translating away, and as they're translating away, they're breaking apart and fine dust is streaming away from them. So that tells us that these are clods of finely cemented material, probably cemented by the vapor deposition of all the micrometeoroids impacting the moon over geologic times. Okay, so this is what it looks like under the nozzle after landing. It's swept clean. This gouge you see here is where the soil contact probe, which was a thin metal rod, where this is where it hit the surface. It was designed to bend up. You can actually, I think that's the edge of the soil contact probe sticking up right there. I'm not sure. But it's about 2 meters long. And when it touches the surface, they get a contact indicator. That's when they're supposed to shut the engine off. They usually didn't. They usually kept the engines going as they descended even farther. Because what good pilot wants to let their vehicle free fall to the surface? But you can see these erosional remnants that are pointed radially away from the center line. And we also see these cracks. Now, this was really interesting. In the Apollo program, they interpreted these as cracks where the diffused gas was coming back out of the soil and cracked it up. But we came up with a new interpretation based on some tests we did in Hawaii. So here we took a rocket thruster to Hawaii and we fired it on the surface. We didn't expect to see anything spectacular. We only expected to get a crater, and we were going to measure the size of the crater. But what we got was a very complex terrain that had been eroded, and the terrain has stair steps. And this was fascinating. So we quickly grabbed cameras and took lots of measurements. This is the original surface. This is volcanic tephra. Tephra is ash that was deposited by airfall. So this is volcanic tephra. It's a rather coarse granular material, but it contains fines that are very, very easily suspended in the atmosphere when disturbed. But upon close examination, we could see that I've labeled these coarse and fine. We could see there's coarse material, and then there's a ridge of fines, and then coarse, and then fines, and then coarse. There's regions where there's no coarse, but we interpreted that as the coarse was entirely blown away. And so apparently there are layers in the soil, and the layers of fine material have more cohesion. And so they resisted the plume better than the coarse material. And so everywhere there was fine material, it resisted the erosion, and you got a discontinuity in the erosion rate. When you eroded down to the next coarse layer, it removed it until you got down to the next fine layer, then you got a discontinuity. And so that created these stair steps. And in some stair steps, the coarse was completely removed, but further away from the impingement point, the coarse was not completely removed. And so we found that very fascinating. Nobody thought that a rocket exhaust could create such fine details in the crater. So we went back to the Apollo landings and we looked very carefully at these shadows. And lo and behold, these are not cracks, these are a stair step. This is a terrace. So this is a flat surface. It goes out to this terrace, and then it steps down about 1 centimeter, and then you've got another terrace. And you can see that this is a very, very long terrace that's very coarse, rough edges. But then over here, we've got other little pieces of stair steps. They're not as clearly defined, but but we do see there's this region that's brighter, and then a region that's more coarse and rough, and then another brighter region, and it's again stair stepping. But unlike the terrestrial test, this is stair stepping downhill as you move away from the nozzle. In the terrestrial test, it was stepping uphill away from the nozzle, and that's because of the difference in the way the plume is. And on the terrestrial test, it was a jet. The dynamic pressure decreases with distance. In this case, there's no flow right here, and the dynamic pressure is increasing as you step away. So you get more erosion as you move further away, up to a point. Okay, so that was fascinating. And this, by the way, nobody had ever predicted there would be laminations in the lunar soil before. So that was another discovery. Apparently, the geology of the moon creates fine laminations with mechanical discontinuities. That has not really been studied yet, but I guess I would have to call this a hypothesis. But I feel pretty strongly that there are likely mechanical discontinuities in the soil column of the moon, and it may be due to the impact cratering history with the space weathering creating some mechanical strength through vapor deposition. Whenever a layer sits there for a long time. So here's from Apollo 12. Again, we see this stair step. It's smooth soiled here. It's rough, cobbly soil out here. And this is the mechanical discontinuity. The nozzle was up here. So again, it steps downhill away from the nozzle, and the coarse material was not completely removed. So that's why the surface looks different. And here's another view where you've got a smooth surface. Out here, you've got a cobbly surface, and this is a discrete stair step moving away from the more elevated terrain. So that was a general feature that we see in these landings, which was fascinating. We also found rocks. The Apollo astronauts made a big deal out of this. They said, hey, look, the rocks don't blow, so we don't need to worry about blowing rocks. And it became a legend, a false legend from the Apollo program that rockets can't blow rocks, and so you don't need to worry about blowing rocks. So we examined this very carefully, and we showed, no, this is an embedded rock. This is the tip of an iceberg, and that's why it didn't blow. And we did see lots of blowing rocks. We see other features like this hummocky, micro scale hummocky terrain. Lots of strange features that we can't completely explain. This is the gouge from the soil contact probe I mentioned earlier. But we see these unheaded erosional remnants. These are erosional remnants that point radially back to the rocket nozzle, but there's no rock at the beginning of each of these remnants. There's no head to them. So again, somehow the variations in the soil mechanical strengths cause the initiation of flow channeling, and then you ended up with these features on the lunar surface by the way the flow interacted with the granular material. And one last phenomena that I want to mention before I dive a little bit deeper into the physics is you can see the landing sites from orbit. You can see that there's a photometric effect where depending on the angle of the camera relative to the sunlight, it can look either darker or brighter around the landing site. And that's because the surface texture of the landing site has been changed, and it affects how the sunlight reflects off the surface. This diameter of this is 150 meters. It's very difficult to explain that. There's nothing in the physics that we know yet that has a length scale of 150 meters. The ejecta is traveling above lunar escape velocity. There are slower particles, but they are in a smooth gradation of quantity versus velocity. And so there should not be an abrupt boundary in the surface effects. I have a hypothesis about it, but this is one of the ongoing mysteries, trying to understand why you get 150 meter diameter brightening. Now, we did see brightening in these tests on the volcano where we fired the thruster, but we think it was from a different effect. we fired the thruster, and after the thruster was done firing, the area that it got fired on was brighter. But this was really fascinating because you could walk over to this and kick it and all the bright stuff would fly away because it was fine dust that had settled on the eroded region. Why would the finest, most easily transported dust preferentially settle in the region where the erosion had been most violent? That was fascinating. We don't completely know, but we have some ideas. It might be electrostatic. Rocket exhaust is charged. Maybe it pulled the dust back, or maybe it was when you look at the erosion features on a smaller scale, you can see this is not a homogeneous brightening, but you see it's very textured brightening with bright areas surrounded by eroded areas. So it may have something to do with the micro scale erosional features. We don't know, but we don't think this is what caused it on the moon. Okay, so why is this important? In Apollo 12, they landed 160 meters from Surveyor 3, as I already mentioned. They walked over on one of their spacewalks, and they cut pieces off of the Surveyor and they brought them back to Earth. This camera is one of the things that they brought back. And this lower part of the camera right here is shown in the right image, and pieces have been cut out, coupons have been cut out, and back in the 1970s, they were analyzed using the tools that were available at that time. We got access to these parts in the 2010s, and we did the first modern reanalysis, so far the only modern reanalysis of the parts. So we were able to use tools that didn't exist back in the 1970s. This is one of the coupons. This is where a washer, this is a bolt hole, and this is where a washer had protected the paint. And you can see the paint under the washer is a different color than the part that was exposed to the lunar environment. When the astronauts walked over to the Surveyor, Alan Bean actually commented, he said, "What color did you say that spacecraft is?" And the Houston mission controller said, "It's white." And he said, "Why do you ask?" And he said, "Because that's not white, it's tan." And that became one of the mysteries. Why did it turn tan? They thought it was due to cosmic radiation changing the chemistry of the paint. We now know that's not true. Okay, so one of the detailed features you see is this shadow right here, which is a crescent shape. I think I show it in the next image in more detail. Let me look. Okay, I don't, but let me explain this shadow. There are numerous shadows on this spacecraft, and they all point back to the Apollo lunar module. So the shadow is the area that was protected from sandblasting. So the sandblasting actually was lightening the surface. It was actually darker this color before it was sandblasted by the Apollo 12 landing. So this is scanning electron microscopy of the area under the washer that was protected. And this is the area that was sandblasted. And the sandblasted has a crack. I'll show you more of those cracks in a moment. And the pigment, the texture of the pigment has been crushed, and there's also lunar dust all mixed in with this. Okay, so we did X-ray photoionization spectroscopy, starting from the bolt hole, moving across the clean area protected by the washer, and then out into the acreage. And when we were looking for 4 specific elements, iron, calcium, magnesium, and titanium, which are in lunar soil, but they're not in the paint. And in the washer, those elements did not exist, but as soon as you get out from under the washer, we see clear indicators of a constant quantity of lunar dust in that region. Now, when we go across the shadow, start from the bolt hole, go under the washer, and then across the shadow, and then out into the acreage, there's actually more of those elements in the shadow and less outside the shadow. So the sandblasted region contains more, the protected region contains more lunar dust than the sandblasted region. And so from this, we learned that the shadow is actually made out of lunar dust, and the sandblasting actually removed dust rather than delivering a net quantity of dust. And so, and that makes sense because the sandblasting was super high velocity, and a lot of the ejecta hitting the Surveyor would bounce off. In vacuum, dust will bounce, just like marbles here on the Earth. Once the drag force is inconsequential, then it behaves like any other geomaterial, and it will bounce. But the fraction that crushes the material and loses kinetic energy by damage will stick. So there is some dust, but there was actually more dust in the region that was not sandblasted. And so this gave us another mystery. How did all that dust get on the surveyor before the Apollo lander got there? Because the lander removed dust. So what put it there? And we don't know the complete answer to that, but we have some ideas. Okay, I mentioned there was cracks in the paint. This is a region where you can see a lot of the cracking, and there are pits, little tiny microscopic holes. This is a laser scan of a pit and a crack. The pits are deeper than the crack. This is an inside out map of that topography. So this is a pit, the pit's deeper, the cracks are shallower, and the pits are correlated to the cracks. So from that, we concluded that the pits caused the cracks, and the pits are all about 100 microns in diameter. So we compared that. Let me see, do I get it? Yeah, I do. Okay, so this is a view of blowing the dust under the lunar module. We got lucky, and there was a frame where there was less dust, one frame adjacent to one that had a lot of dust. And that, because of that lucky effect, we were able to take the dark and the bright side of this rock, both with and without dust. And that enabled us to cancel out all the unknowns about the film and the camera. And from that, we could quantify the amount of dust in this one frame of the video. And then with some wild extrapolations and lots of hand waving, we could come up with a very crude estimate of how much soil was being blown. We used the particle size distribution with that quantity of blown material. And then we said, well, let's assume that particles with a certain kinetic energy per impact area are able to penetrate the paint. And we tried it again with momentum per impact area. And when we use that sort of a model, either way, either one of those models gave us about the same answer. It predicts that we would get a spike of, this is the diameter of the pits that we would get, and this is the number of pits per square micron of size. And it gave us roughly the correct size distribution on the pits. However, there should have been 1,000 times more pits on the surveyor than what there actually were. And again, as I showed at the beginning of this talk, most of the spray went harmlessly over the surveyor. And so that's why the damage is a factor of 1,000 less than if it had been in the main spray. And so the surveyor was only damaged by particles that were scattered out of the main spray by particle collisions. And I'm going to go back to this picture here, because I think you can see that the damage, the sandblasting is modeled. It's not uniform. And the size of one of these models is, I forget the numerical value of that size, but we projected the angular size of this relative to the center line of the lunar module. And when you project that size, that angular wedge back to the region where the erosion was taking place, the diameter of that wedge at that point is smaller than a single dust speck. So in order for it to get this correlation of sandblasting, spatial correlation of the impacting particles, the correlation could not take place at the point of erosion. They had to take place in transport. And so that's evidence that granular collapse was occurring in transport. The particles were colliding and they were clumping together, and it gave us this modeled sandblasting rather than a homogeneous sandblasting. So that's very rough hand wavy argument, but that's prima facie evidence that particle collisions are important in the cloud. Okay, I'm going to skip over a little bit of this to get to some of the more fun physics, but we've done sandblasting tests with lunar soil. It's very abrasive. It eats right through lots of different materials, damages glass. And so this is why it's important. We need to understand how much damage will occur in lunar landing so we can prevent it. Okay, so to do more analysis, we needed a model of the size distribution of lunar soil, including the submicron fines. There are not good references in the literature that give us the entire size distribution. We've got size distributions of everything bigger than a micron, and we've got size distributions of everything smaller than 10 microns, but nothing that covers the whole range. So we've tried to merge these data sets together. There is a gap right at the point where the data sets meet, which is probably an artifact of the measurement methods. We can measure that rocks are blowing. We know because of simplified modeling that the sand and dust go so fast, some of it can escape from the moon. The Apollo astronauts reported that the horizon was became fuzzy during landing. And because the horizon was fuzzy, that tells us that the dust was going higher than their view of the horizon and right out over the horizon. We're not sure if the dust-sized particles cling to the larger particles or if they separate. And that makes a huge difference in our efforts to quantify the erosion rate, because the dust-sized particles contain a huge fraction of the optical density of the lunar soil. So if the dust-sized particles cling to the large ones, then it'll reduce the optical density for a given mass flow rate. And then our attempt to convert optical density into mass flow rate will be skewed. Okay, where do they go and how fast? Well, as I mentioned, we measured the elongation of the footpad shadows. Also, this is the shadow of the soil contact probe right here. And this is the shadow of it again on top of the dust. And you see the two shadows are at different angles. And you can directly measure the angular difference. We've done scale model simulations, physical model simulations of blowing dust to measure footpad elongation. We've done simulations of it. And here's the geometry. And so based on all of this, we actually have to take measurements of an actual lunar module, because they don't have good CAD drawings from the 1970s, of course, not computer-aided ones. But based on that work, we were able to calculate the angle that the dust cloud is blowing away from the landing site. And on all the well, we couldn't measure Apollo 12 because the sun angle was too low and the shadows were too long and they exceeded the field of view of the camera. But all the other landings, except for Apollo 15, the dust angles were between 1 and 3 degrees. Apollo 15, it was like 8 to 12 degrees, which was surprising, but we think we understand that. Apollo 12 landed over this broad crater. It was translating forward as it landed. It landed right on the rim of the crater, and after it landed, it rocked backwards 12 degrees into the crater. So that dust was ramping up out of that crater, and so what we're seeing is the shadow difference after it comes out of there. So we think that's why it was the oddball, the exception. In general, the dust blows 1 to 3 degrees, which matches our simulations. For velocities, we can't get any empirical data from these videos, except for the rocks. By doing these computer simulations, one particle at a time, neglecting particle collisions, we calculate the velocities that are achieved at different particle sizes for different cases, different heights of the lander, different size particles, different beginning points for their trajectories. And we're getting that the angles they travel is between 1 and 3 degrees. So we had excellent correlation with the empirical data. This simulation gave us velocities up to about 1,500 meters per second. Now, the simulations are not good at giving us an accurate prediction here, because there's a lot in the physics that we don't have modeled that well. Mostly it's the boundary layer. The boundary layer is very difficult to model. And so how the particles are lifted up through the boundary layer dramatically affects the velocities that they achieve. And so it turns out these simulations are not that accurate. But we've created a parameter space to try to predict velocities for different parameters. Now this was I showed you this simulation at the beginning. This simulation predicts 3,000 meters per second. Other simulations, people are saying 200 meters per second. So we're getting an order of magnitude of uncertainty in these different simulations. But on the overall assessment of all the simulations, trying to integrate it all together, our best estimate is that particles are going in multiple kilometers per second and probably exceed lunar escape velocity. But whether they exceed lunar escape velocity or not, they certainly travel higher than orbital altitudes on the moon. So this is a particle going 1,900 meters per second. It leaves the moon here. It crosses the orbital altitude of the Apollo Command and Service Module, travels all the way around the moon. It crosses that altitude again, and then it impacts the moon here. And then particles going other directions have the same thing. So you end up with a circular intersection point and then another circular intersection point, where if you happen to be crossing either of those 4 points, if you happen to be crossing any of those 4 points with your spacecraft with unfortunate timing, you will get sandblasted, not just by the ejective velocity, but by the net orbital velocity. And so that exceeds 4,000 meters per second, which is in the hypervelocity regime. So you'll get sandblasted at hypervelocity with hypervelocity physics, which causes vaporization and melting of target material. Okay, so we've measured the blowing of the rocks. Here's an example where we've measured the shadow for size reference. We've got a rock on the ground for our location reference, and then we're going to track this rock in the lower part of the image in multiple frames. And so we've done this for as many rocks as we could find in the videos, and we're seeing 4 centimeter rocks going about 30 meters per second, which is interstate highway speeds. 10 centimeter rocks are going about 25, 35 miles per hour. The trajectories are in really good agreement. So the trajectories, our trajectory models, we're predicting the rocks accurately. Okay. At what height does the blowing begin? Well, most times they reported 100 meters. Apollo 12 said 300 meters. Our best theory is that Pete Conray got confused. He was thinking 100 feet. He was thinking 100 feet. He later on in his head got confused and thought it was 100 yards. And then he converted it back to feet and said 300 feet. So I think that's what happened. Other than that, it was always around 100 feet where the blowing started. So roughly 30 meters. We've done shear stress calculations of the rocket exhaust, and we actually used Carl Sagan's research for blowing dust on the moon Triton in the outer solar system, as well as other models of blowing soil, and tried to estimate what is our best estimate of when erosion should occur. It's different particles are erodible, more or less erodible based on a combination of their cohesion and their weight in this gravity field. But the most erodible particles is about 100 micron size. And so in this particular simulation, they were nearing threshold of erosion. I don't want to take the time to explain all of this, but it's just simply comparing the shear stress in the gas with the forces that will hold the particles down. So it also is going to depend on the thrust. Larger vehicles will have obviously more shear stress. Multi-engine effects have not been assessed, but where multiple engine plumes intersect on those plume reflection planes, you get enhanced shearing. So we said for now, 40 meters is our estimate. If you want to land near the Apollo sites, you can't go lower than 40 meters when you're in sandblast region. Okay, how much material is blown? We've done lots of experiments. And by the way, Surjit, I don't have a good estimate of the time here. What?
Oh, we have about 15, 17 minutes or so.
Okay, is that including Q&A, or do you want me to finish talking?
No, finish talking.
Okay.
Yeah. Thanks.
Okay, so we've done the experiments. I mentioned experiments on the volcano. We've also done them in large vacuum chambers where we set up experiment boxes with a camera that would rotate from one box to the other, because that way we could only afford to pump the chamber down once per day, so we could get in multiple experiments that way. We've used hot fire thrusters in deep sand beds. We've done reduced gravity flight testing to look for gravity scaling. I mentioned we've tried to scale it from the optical density, looking at the optical properties of lunar soil, doing the light scattering. We've done those calculations. The total eroded soil, varying all the different parameters, we're estimating somewhere between 2 to 8 tons of soil were blown on each landing. Now we've come up with a more, we think, a better method to estimate it. Rather than looking for discrete rocks, we're using a statistical method where we look at the pixel brightnesses. Some pixels are bright, some are dark. The altitude of the lander shouldn't have much effect on that. The histogram of bright and dark pixels ought to be about the same, whatever altitude you're at, based on the power law size distribution of the craters. And so here's an image with a lot of dust. Here's an image without a lot of dust. The histograms are very different between these two videos. So we can synthetically subtract dust from the image using an equation to enhance the contrast pixel by pixel and try to make the histograms match. And if we can make the histograms match, then what that tells us is the amount of dust we had to synthetically subtract is the total amount that was in this image. because we're comparing to an image that has no blowing dust. Or we can do it the other way. We can synthetically add blowing dust until these two histograms match. Either method ought to work. So we developed this method, and researchers in China have improved upon the method, and they recently published a paper where they're doing a better job than we originally did. We had put in some assumptions for our first effort, and they were able to go beyond those assumptions and take them out. But so using this method, this is a plot of the erosion rate versus the altitude of the vehicle, with the squares where the erosion, I'm sorry, this is the shear stress. The shear stress was determined by computer modeling as best as we can do. The white, the open circles are the measurements of the erosion rate of soil, the flux of soil. And then the black circles are so we did a curve fit to this equation, and then we tried to use we tried to create solutions at the same points where we had simulations predicting the shear stress. So by doing that, we came up with a relationship which says the erosion rate is proportional to the shear stress to the 2.5 power. And that makes no physical sense. I've spent years, we published this in 2014, I think it was, or 2015. I've spent all the time since then trying to figure out how in the world can you get 2.5 out of the equations of physics, and I can't do it. So I think that the assumptions we used induced a bias which tricked us. And some of the more recent work that NASA is doing, which I can't show yet because they haven't published it yet, suggests that this really should be unity power. But it's interesting that we've gone for several years being fooled into thinking the erosion rate is 2.5 power law of the shear stress. Okay. So anyways, using this method, even with the shear stress power law of 2.5, we predict about 2.6 tons of soil would be blown, 2,600 kilograms, which is in decent agreement with previous estimates. And so even though there's a huge amount of uncertainty about this equation for shear stress, we still think we have a pretty decent guess of how much soil blew. One of our estimates was based on just looking at those layers. I mentioned the stair-step layers, and by looking at the thickness of the layers and then estimating how many layers were removed and over what radius, then you can very crudely get a hand-waving estimate of the quantity of soil that was eroded. And that method is also in agreement with this. Okay, so where does the soil strike the surface? We've done lots of computer simulations. I'm sorry, some of the fonts didn't translate, but this is in meters of distance. So 2,000 meters away, we're looking at milligrams impacting per square centimeter, or we're looking at square centimeters of impacting material, the surface area of the impacting material per square centimeter. So you get complete sandblasting, 100% sandblasting all the way out to like 60 meters. The surveyor was, we have one data point of actual ground truth of the surveyor. It was a larger thrust vehicle than any of these. And also it was outside the main spray. And when we take those factors into account, it seems to be in crude agreement with our predictions. So anyways, even all the way out to 20 kilometers, the flux is non-zero. That little ribbon should be a negative. So 10 to minus 4, 10 to minus 5 milligrams per square centimeter. So it's a very low flux, but it's non-zero even 20 kilometers away. And indeed, it should go globally on the moon. So the flux never goes to zero. It just gets smaller as you move farther away. So we have a very crude estimate of about 3 tons of soil were blown for each lunar module landing. Depends on the environment very heavily. The turbulent kinetic energy is not normal due to the rarefaction of the plume. So the erosion rate is not the same as on Earth. The lunar soil and the gravity are not the same. The soil cohesion is not well understood in that environment, exposed to the plasma environment of space without an atmosphere, without a dense atmosphere on the moon. The charging environment is not well understood, and we've never had an instrument to directly measure it. Our estimate depends on the particle velocities. It comes from a few optical density data points. We know how to improve this, but we need funds. We need to put instruments on the moon. Okay, I'll briefly mention that multiple engines will cause enhanced erosion at the plume reflection planes. We've done modeling of this, and we actually saw it. I'm sorry I didn't include the picture, but the recent sky crane landing of Perseverance on the moon, we actually saw dust. Looking down during the landing, you could actually see a wall of dust between the engines where the dust was accumulating on that plume reflection plane. Shock effects. Oh, that's another video. Okay, I'm going to skip over the chemical contamination. And I just want to make a few comments about the physics. There's in the modeling, there has been a lot of progress because of the work of Jennifer Curtis. She is now at the she's now at one of the California universities. I forget which one, but she, last I knew, was the dean for research at University of California, I think maybe Fremont, but I'm not sure which one. But Jennifer Curtis has done discrete element modeling, and that her work was converted into shear stresses for different conditions and was put into one of NASA's flow codes. And then also the work of Dufty at the University of Florida, Garzo, I don't know where Garzo is located. So Garzo and Christine Hrenya at the University of Colorado Boulder. So Garzo, Hrenya, and Dufty wrote a version of the Boltzmann transport equation for granular gases. And so it's called GHD theory after them. And so Jennifer Curtis worked together with a company called Computational Fluid Dynamics, CFD Research Corporation, to put GHD theory, as well as to put Jennifer's DEM results into this higher scale code. So the code is called the gas granular flow solver. Now, it can't directly solve GHD theory because it's too computationally intense. So they created fast lookup tables. So in each cell of the code, they can look up the GHD results for that cell. And so right now, NASA is benchmarking this code to see how well it correlates to experiments. And so some of the funding I have right now is to take experimental work and provide it in a form so they can compare the GHD code. So that's the current state of the art. But the the gas granular flow solver does not include any turbulence modeling. It is unable to identify surfaces because it's a volume of fluids method. And because it's unable to identify surfaces, which are singularities, singularities in the density, therefore it cannot, in my opinion, it cannot predict granular sublimation, direct transition from solid-like to disperse-like behavior. It assumes that it goes from solid to liquid to gas. And if everything did that, then in theory, the code should be pretty good. But I think because of these inadequacies, I don't think we yet have a code that can actually predict the physics. But we're trying to find out, is it good enough for now? But we have had focus research, as I'm reading the chart now, for a decade, when this presents a compelling picture of the main physics in the lunar plume effects. The effects are more severe than we previously realized. The terrestrial common sense does not expect the extreme sandblasting for such a far distance away with extreme velocities. Surveyor 3 underrepresents the effects because it was below a factor of 1,000 less sandblasting because it was below the main sheet. So it gave us a false image. And we know the prior literature from the Apollo era uses pre-computer methods that we now know were not correct. They roughly guessed the erosion rate and they got it roughly correct back in the Apollo era, but they used wrong physics for that prediction. Our basic understanding is adequate, we think, for now to protect the historic sites on the moon. So we've created ground rules for landing on the guidelines for landing on the moon. but much more research is needed. We need to improve our understanding of the physics. We need to develop computer-based models that are computationally tractable. Brute force methods are intractable. We need to find equations of physics so that we can manipulate those equations into a form that are tractable in a large-scale computer simulation. And this is really high-value research to support future spaceflight objectives. One of the reasons that this is so important is because it's going to involve international conflict. When countries land on the moon near each other's hardware, they're going to be damaging each other's hardware, which is not allowable by the Outer Space Treaty, but it's unavoidable. We cannot avoid damaging each other's hardware when we land on the moon. So we need to have international agreements on how much damage is allowable and when are you required to build a landing pad so that you don't cause excessive damage. How do we notify each other in order so that countries can prepare for the sandblasting ahead of time, protect sensitive instruments. So this is an international cooperation issue, and it's going to involve geopolitics, and it puts physics right in the middle of this geopolitical question. We need to understand the physics so that we can come up with a good series of solutions for the geopolitical problems. Okay, so that's my talk. I hope you found it interesting. And if we have time, I will be happy to do questions.
That was very, very nice. Fantastic. Really entertaining, and also some brand new stuff. So we are open for questions. Let's go for it.
Suraj, can I ask a question?
Yeah, go ahead, Kimani.
So how much of these transport properties that you have outlined is common with meteorite collisions on the moon?
That's a good question. So when the surveyor was pieces of the surveyor were first brought back from the moon, they wanted to bring it back so that they could study how many meteorite impacts were on the hardware. And what they found, they did not expect the severe sandblasting. They thought if they land 500 feet away, so they landed 160 meters, they thought if we land that far away, there shouldn't be any sandblasting damage. Well, they were grotesquely incorrect in that. I mean, it was severe sandblasting. It turns out that they couldn't definitively identify any micrometeorite impacts on the surveyor. There are a few that might be, but the vast majority of all the craters on the surveyor were caused by the sandblasting of the Apollo 12 landing. So now we know that when you're on the moon, you are going to be damaged by micrometeorite impacts. So your hardware has to be able to withstand that anyways. And if we can create the if we can limit the sandblasting damage to some fraction of the natural flux, then we should be able to say that's low enough, then, and it's acceptable. But we got to remember damage is cumulative. So maybe we need to say the damage has to be, maybe we'll say 10 years of natural flux is acceptable. And so each landing has to provide 1/10 of that so that you can have 10 landings. So we have to do some calculation like that when we come up with an agreement on how much damage is allowable. Now, there's also an issue of secondary ejecta. When impacts hit the moon, they blow out ejecta, and then the ejecta hits the moon a second time. So those are called secondary impact craters. And there's been a lot of work recently trying to quantify the secondary ejecta on the moon. And that modeling has improved our understanding of the soil, because the soil gets flipped over by all the impacts, and that causes the weathering. So those are low velocity impacts, relatively low. These rocket exhaust effects are in between. So a hypervelocity impact from interplanetary dust is going to be around 12 to 17,000 meters per second, whereas the ejecta from a rocket landing is going to be somewhere between 400 to 3,000 meters per second. And then the secondary ejecta are much slower than that. I don't know the numbers, but below 100 meters per second, maybe. So there's a lot of flux on the moon, different particle sizes, different velocities. And so our modeling has to take all that into account.
Thank you very much. I enjoyed your talk a lot.
Okay, good.
Yeah, Human.
I have a question. Two words catches my attention. One is that turbulence, and the other is the power law. Okay. So, but you said that what your simulation model does not include turbulence.
Right. It's because the gas flow models that handle rarefied flow, they do not have turbulence models. So in continuum flow, we have Reynolds average Navier-Stokes where you're averaging over the turbulence, and then you add a turbulence model, one of the various turbulence models that are available. And there are all kinds of different, I'm not an expert on this, but there's all kinds of different turbulence models. Some assume isotropy, some are anisotropic turbulence. And then we also have large eddy simulations where you can actually model the largest features of the turbulence explicitly. But the problem in these rarefied flow cases is that the mean free path length becomes longer and longer. And so the grids in your simulation are typically smaller than the mean free path length of the molecules. And so there's not going to be any subgrid turbulence in that case by definition, because the particles can't collide in a loop smaller than the grid. But we're trying to go from continuum to rarefied. And then, as I mentioned in the talk, in the flow field, it actually goes back to continuum again and then back to rarefied again. So in the region where there can be turbulence, we're trying to model from a continuum flow, which can have turbulence. Typically, coming out of a rocket nozzle, it's not turbulent. It's invested flow, just because the way the flow developed, there hasn't been any triggering of turbulence. But then it flies through a region where we're not going to model the turbulence, and then it's going into a region where we can model the turbulence, but we typically don't, because going from a rarefied flow back to a continuum flow is problematic. The models use different time steps. They have different types of stability criteria. Reynolds average Navier-Stokes tends to be rather unstable. It's difficult to get it to converge, whereas the rarefied flow models are very noisy, and so you're injecting noise into a borderline unstable model, and so it won't, there's all these problems, practical problems in the modeling. And so typically nobody has ever tried, to my knowledge, to include turbulence in any of these rarefied flow transitional flow cases. And I keep bringing this up over and over again, that turbulence is really important here, because in terrestrial erosion, the turbulent kinetic energy is definitely a driver of the erosion rate. And so, it's the splashes of turbulence hitting the surface that are liberating particles and contributing to that rate. So, so we know there's a major gap. So I keep telling the modelers that the models you've developed so far cannot predict the erosion. I mean, you can say, well, we're just going to use whatever erosion naturally develops in our model and see if it's good. And I'm like, well, okay, if it's good, it's only because you got lucky, because you don't have the right physics in your model. And so I keep telling them that really we need to have a semi-empirical model. You need to measure the erosion rate in that environment and then have a way to put the erosion rate into your model by hand, because right now the model doesn't have the right physics to predict erosion rate. Until we can get better models. So, but that's one of the disagreements. There's the old saying in NASA, at least, that nobody believes the model except the modeler. Everybody believes the experiment except the experimenter. And so that's kind of the way it is. The modelers, they really believe in their models, and the experimenters are not so trusting.
Okay, one more question. If you want to use the Reynolds number, right? Reynolds number to characterize all these regions, how do you like this region? Is there an inertial range in all these turbulence models?
You broke up in the middle of that.
Yeah.
Yes. If you look at all these flow regions, what is the Reynolds number for all these flow regions?
Okay. So you're breaking up again, but I think I understand the question now. So I've seen people use different Reynolds numbers. Like, what is the length scale that you want to use in the Reynolds number? And so in a lot of the experiments, terrestrial small scale experiments, they'll use a Reynolds number based on the diameter of the jet orifice. And so in those experiments, I'm trying to remember what the typical Reynolds numbers. It's been about a half a year since I've looked at it, and I already forgot the numerical values. But if I recall, in the region where erosion was taking place, it was predicting rough turbulent flow. So the Reynolds number was large enough that it should have been rough turbulent. I don't remember what the values were. But in these studies of the lunar case, I've seen people use other Reynolds numbers. Like you can use the height of the shock wave above the surface as your relevant length scale. I've seen the height of the vehicle above the surface could define a Reynolds number. But I don't know. Jen, I guess your question is, what are the numerical values in all these different regions? And I'm sorry, I really don't know. I can tell you though that the flow is going about 6 times the speed of sound of the gas, the sound in the gas. So the exit velocity of the gas is about Mach 6. So it's definitely fast enough that if you triggered turbulence, then turbulence could develop. However, typically coming out of a rocket nozzle, it is inviscid, non-turbulent flow in that region. And then here's the question, and we've had this discussion in our team meetings. The rocket exhaust is inviscid. It goes through shockwave, becomes subsonic. It's zero velocity, so Reynolds number is 0 in theory at that impingement point. And then it speeds up as it moves away from the impingement point. As it speeds up, the Reynolds number is increasing. And then it's flowing over rough soil, so you can trigger turbulence. But it's also becoming rarefied. And so the mean free path length is getting longer. And so the question is, does it become turbulent before it becomes too rarefied to be turbulent? And is it turbulent, at least to some degree, in the relevant region where the erosion is taking place? So that's the question. To my knowledge, nobody knows the answer. To my knowledge, nobody's done a proper study of it, but we have argued about it.
Okay, we have a question from Arijit. Arijit, go ahead.
Yes, my question is about what could be the practical solution when many countries would actually like to land on moon. Would it be just building landing pads?
Yeah, that's a great question. Yeah, so there are a lot of different ideas to try to solve this problem. And I firmly believe that we're going to have to build landing pads on the moon. But the question is how often and where, and are there cases where you don't need a landing pad? If we always require a landing pad, that means you can never take a big rocket somewhere unless you've already sent a small rocket with equipment to build a landing pad first. That's very restrictive. And so of course, everybody doing mission planning wants to resist that. And so they all want to just take the big rocket straight there. I mean, what good program manager would not resist the idea that you have to put into your program plan all these additional steps, right? So, it's not a settled question. In fact, the United Nations has been discussing it. A friend of mine, Michelle Hanlon, from the Center for Air and Space Law at the at Mississippi State, I think, or University of Mississippi, she has a nonprofit called For All Moonkind, which is focused on preserving the historic sites on the moon. But she's branched out into the larger issues of sandblasting on the moon. And so she actually has a permanent observer status seat at the committee of the UN. And they periodically argue about this, but they haven't made much progress. As you can imagine, progress is going to be very slow. And I think what's going to happen is we're probably going to have case law established first. Countries are going to be landing on the moon before the UN ever comes up with any solutions, I think, sadly.
Absolutely.
Yeah. But so it's going to be decided by countries wrestling. Hopefully wrestling in a peaceful way. So the United States has already staked out its position. NASA put out this document called the Artemis Accords. And the Artemis Accords, it doesn't have a lot of specifics, but it includes this idea that every country gets a zone of influence around their activity on the moon. And so that zone of influence, other countries should not interfere with what's going on in that region by sandblasting other things. So some countries have disagreed with that and said that's a territory claim. But NASA is saying, no, it's not a territory claim. You know, you're welcome to come in and inspect, and we're not claiming the territory, but just don't interfere with what's going, you know, so. Okay, anyways, it's being decided. So
you need an interference passport for it.
There you go. Yeah, issue visas to visit your location on the moon. And who knows, that might happen. Okay, but some of the potential solutions is you can build landing pads by sintering the soil, microwaving it, or using solar concentrators. You can add polymer to glue it down, but the polymer breaks down under high temperatures, so it's a one-time use landing pad. You can make bricks in ovens. People have been prototyping a lot of these methods and studying them. I've done a trade study, which we're in the current process of publishing. And our trade study says microwave sintering actually trades very well. I didn't used to believe it, but in the analysis, it actually shows up that microwave sintering is really good. Once the cost of putting hardware on the moon goes below $20,000 per kilogram, which will be, you know, in the distant future. But once it gets below that cost, then you can deliver polymer and just polymerize the outer regions of your pad and sinter the inner zone. And that becomes a cheaper method. The cost of building a landing pad right now with current launch prices is almost $1 billion to build one landing pad, which is a lot of money. We think when if SpaceX Starship starts landing on the moon, if it brings costs way down, that cost should be coming down. We think the cost should get down to about $50 million per landing pad. But that's still a bit of money. You know, that's about half the cost of a cheap planetary lander. So it's a significant investment to build landing pads.
I actually had another question. I mean, you have not taken into account turbulence, in this modeling. Now, can you put some sort of an, lower limit as to what extent thermalization due to, turbulence would make the particles deviate from the trajectory that you have shown? The ones are blown off, comes back and hits surface of moon again. So that can, to what extent that can change it?
Yeah, I'm afraid that our abilities at this point are far below the ability to do that. We just do not have the capability to make those sorts of estimates. The modeling that we have predicts everything moves straight radially away from the lander. The boundary layer modeling of the boundary layer is not very good. You know, I mean, we're neglecting turbulence. So how good can the boundary layer be, you know, in our model? The velocity the particles achieve depends critically on how high and how rapidly they get lifted through the boundary layer into the higher velocity gas. And as the particles are being lifted, they're also running out into vacuum where the drag force is decreasing. So they reach an asymptotic velocity. But the quicker they get up through the boundary layer, the higher that asymptotic velocity is. So without being able to model the boundary layer accurately, we just don't have the ability to predict these things. We have the empirical data from the Apollo landings, but we've never had a dedicated instrument land on the moon to get good measurements. We've talked about using all kinds of different instruments to make these measurements. I'm working on a laser-based sensor where we want to use multiple lasers. We think we can actually extract the particle size distribution from the lasers if we use about 8 wavelengths, 8 wavelengths with lasers spaced closely together like guitar strings. By looking at the scattering in the adjacent beams, there are algorithms. We've tested these algorithms where you can invert the scattering matrix and get out the particle size distribution. Then if you add Doppler filters, we may be able to get velocities as well. But this technology is a NASA uses a scale of 1 to 9 for technology readiness, and this instrument is about a 3.5. So it's going to take a lot more work to get the instruments ready to go to the moon. And then we have to convince NASA to put them on the landers. So it's a lot of work needs to be done.
I have a comment. Sorry, Arijit, you had a question?
No, it's done. Thank you.
I have a comment that I wanted to make before we run out of time. So it is obviously the case that it is very difficult to put in turbulence because of the very reason that we don't understand turbulence very well to begin with, right? Mm-hmm. However, one can use lattice gas type techniques in 3D. And because you have a fair amount, in fact, you have a lot of freedom in the modeling process, you can bring in the combination of fluid dynamic behavior, combination of particulate behavior, and along with it, combine observed behavior. So I just don't understand why with these three things, it hasn't been approached, or has it been? Because it seems like it's silly to have gone completely the continuum route and not going the route which has the advantage of incorporating everything in.
Well, the last I knew, the lattice methods were not yet applied to supersonic flow. I haven't kept up with that field of research, so I'm not sure yet if they can handle supersonic flow or not. And so another factor on this is that I'm not one of these modeling people. You know, I'm more of an experimentalist theorist, and I do experiment and theory, but I don't do the hardcore modeling. So I don't have the ability to develop these kind of models myself. So we use the models that we find available in the literature, and we NASA has put out numerous solicitations, and they worked with several companies. One company was using it's a statistical approach to the Boltzmann transport equation, where it doesn't do the I forget what that formalism is called, where you do the integration over the Chapman-Enskog.
Okay.
So Chapman-Enskog integrating over the Boltzmann transport equation, you get Navier-Stokes. So rather than treating it like Chapman-Enskog did, it's a different treatment of the Boltzmann approach and Boltzmann transport equation. And you end up with a probability distribution approach to the gas behaviors. And so that method is known as the Unified Flow Solver. CFD Research Corporation offers it as a commercial product. But it doesn't handle the particulates. You know, it's only the gas phase. And then CFD Research Corporation. So we had lots of arguments whether or not you should do Eulerian for the particulate phase or Eulerian Lagrangian. Yeah. The problem with the Lagrangian approach is there's just too many particles. Like if you have a cubic centimeter of lunar soil, once you include the particles that are down to 10 nanometers, a hundredth of a micron, there's trillions of particles in that cell. So you have to truncate it, either truncate it and ignore the finer particles at some point, but can you truncate it? If you truncate it to where it's tractable, there's few enough particles, how much of it are you throwing away by throwing away the finer ones? And so that's why Jennifer Curtis and Christine Hrenya and others, Peter Lever, did an Eulerian approach, which is, I mentioned the gas granular flow solver. So they did GHD theory, and then they put it into an Eulerian framework. Now, Christine Hrenya showed that if you treat lunar soil as 9 fluids, each fluid is 1 particle size, then it gives you a very accurate representation of the full particle size distribution. So in this Eulerian approach, they use 10 fluids, 9 of them are particle sizes, and the 10th one is the gas, the actual rocket exhaust gas. But trying to do 10 intermixed fluids, each with their own transport physics and all the cross transport physics, it's not
hard.
tractable.
Yeah, but Christine is very good, and yeah, so it makes a lot of sense to go that way. But given the scales you have, it seems like, you see, the problem with any kind of lattice-based simulations is that it can give you, while it can give you a continuum and did we lose him? Oh no, he said, while it can give you both continuum and particulate physics, while it can give you everything, there is a fair amount of focused experimentation that needs to be done such that the laws are developed right. Now, once the laws are developed, it would seem to me that it's largely a one-time investment. So